Right now, deep inside a classified facility in California, machines are being built that will never touch Earth again. These are not ordinary robots. They are engineered to survive temperatures of negative 195 degrees Fahrenheit, dust storms larger than entire continents, and a silence so complete no human has ever heard it. This is NASA's robot factory, and it is unlike anything on this planet. Mars is 140 million miles away. No human has set foot there. No rescue mission can reach it in time. So when NASA sends something to Mars, it cannot fail. Not once, not ever. The machines being built right now inside these walls are designed with that one terrifying truth in mind. Perfection is not a goal here. It is the only option. What does it actually take to build a robot for another planet? How do you test a machine for a world you have never visited? And what happens when a robot's NASA is building today becomes smarter than the engineers who designed them? Stay with us, because what you are about to see will completely change how you think about the future of exploration. Welcome to the Jet Propulsion Laboratory, JPL, in Pasadena, California. This is NASA's nerve center for robotic space exploration. Founded in 1936, JPL has been the brain behind nearly every unmanned mission NASA has ever launched. Mars rovers, deep space probes, planetary orbiters. They all began right here, inside these buildings, in the hands of some of the most brilliant engineers alive today. JPL operates on a budget of over $3 billion annually. It employs more than 6,000 scientists, engineers, and technicians. But the number that truly matters is this. JPL has a 100% mission success rate on Mars surface landings since the year 2004. That streak did not happen by accident. It happened because of what goes on inside this factory every single day. Why does any of this matter to you? Because the robots being built at JPL are not just going to Mars for science experiments. They are paving the road for human colonization. They are testing the soil, analyzing the air, scanning for water, and mapping the terrain. Every robot they send today is preparing the ground for the humans who will follow. Your children's future may depend on what is built here right now. Walk through the main entrance of the JPL manufacturing floor, and the first thing that hits you is the smell. Clean, almost sterile. The air inside the facility is filtered to remove particles as small as 0.3 microns. That is smaller than a human blood cell. Because on Mars, one microscopic or contaminant could compromise an entire scientific mission. Cleanliness here is not optional. It is law. The facility operates inside what engineers call a Class 10,000 clean room. That means no more than 10,000 particles per cubic meter of air. Workers wear full white suits, called bunny suits, gloves, booties, and face masks. No food, no drinks, no jewelry. Even breathing patterns are controlled. This is the most pristine manufacturing environment outside of a hospital operating room, and it runs 24 hours a day. Raw materials arrive here from across the country and around the world. Titanium from Japan, carbon fiber composites from Germany, radiation-hardened microchips from specialized American manufacturers. Each material is tested multiple times before it ever enters the clean room. A single batch of faulty aluminum could mean a robot arm failing 60 million miles from the nearest repair shop. Every gram of material earns its place here. The structural frames of Mars robots are machined from aerospace-grade aluminum and titanium alloy. These machines must endure launch vibrations powerful enough to shake a skyscraper apart. They must survive the freezing vacuum of space for months. Then they must slow from 12,000 miles per hour to zero in just 7 minutes, NASA's infamous 7 minutes of terror, and land softly on another world. The engineering required for that is breathtaking. Over in the machining bay, industrial CNC mills carve robot chassis components with tolerances measured in thousandths of an inch. A single structural bracket for a Mars rover can take over 40 hours of precision machining to complete. The cutting tools were down and are replaced mid-operation by automated tool changers. Human engineers monitor every pass on digital screens, watching numbers that must never deviate. One wrong cut, and the part is scrapped entirely. But here is something most people never consider. When a part is scrapped at JPL, it is not simply thrown away. Every discarded component is analyzed. Why did it fail? Was it the material, the machine calibration, the temperature in the room? JPL engineers call this process failure archaeology. They study every mistake like detectives at a crime scene, because understanding failure is how you guarantee future success. Nothing here is wasted, not even the errors. Now we enter the robotic arm assembly station. This is where the mechanical limbs of Mars robots come to life. A single robotic arm for a rover like Perseverance contains over 15,000 individual components. Motors, gears, sensors, cables, thermal protection layers, and structural joints all packed into something roughly the size of a human arm. But this arm can drill through solid Martian rock. No human hand can do that. The joints in a Mars robot arm are engineered to move with extreme precision at temperatures that would shatter ordinary metal. Each joint motor is tested in thermal vacuum chambers that simulate the surface of Mars, -80 degrees Celsius during the night, rising to 20 degrees during the day. The motor must perform flawlessly through thousands of thermal cycles before it ever earns clearance to leave this building. Most motors fail long before they get there. Inside the electronics lab, engineers wire circuit board by hand, using tools and techniques that have not changed much since the Apollo era. Not because NASA is behind the times, but because human hands still offer something no machine can: adaptive judgment. A skilled technician can feel resistance in a wire connection. They can sense when a solder joint is slightly off. That intuition is irreplaceable, even here in one of the most advanced facilities on Earth. Every electronic component used in a Mars robot is radiation hardened. The journey through deep space exposes electronics to cosmic rays and solar particle events that would instantly destroy the chips inside your smartphone. NASA sources specialized radiation-resistant chips manufactured in small batches by a handful of American companies. These chips cost hundreds of times more than consumer electronics, and they are tested individually, every single one, before installation. Let us pause here for a moment, because what you are witnessing is not just manufacturing. It is a physical translation of human ambition into metal, wire, and code. Every bolt tightened in this room, every circuit soldered, every gear fitted into its housing. All of it exists for one reason: to extend the reach of humanity beyond the limits of a human body. This is not a factory. This is a launching pad for our species. Now we move to the wheel fabrication bay. Mars rover wheels are engineering masterpieces. The wheels on the Perseverance rover are made from aerospace aluminum, just 1 millimeter thick, yet strong enough to roll over jagged Martian rocks without collapsing. They are not inflated like car tires. They are solid, flexible metal rings. Each wheel took over 2 years to design, prototype, and test, and they are made to last at least 1 full Martian year, nearly 2 Earth years. You might be wondering, if the wheels are so strong, why do rover photos from Mars show dents and holes in them? Good question. Early rover wheels like those on Curiosity experienced unexpected wear from sharp Martian rocks. Engineers call those rocks gatorbacks. The damage was not catastrophic, but it was humbling. So Perseverance's wheels were redesigned. Thicker, rounder, more resilient. That is how NASA works. Every mission teaches a lesson, and the next machine reflects it. Deep in the heart of the facility is a room most visitors never see. It is called the ATLO Bay Assembly, Test, and Launch Operations. This is where individual robot components come together for the first time as a complete system. Engineers lower chassis frames onto suspension systems using precision overhead cranes. Robotic arms are attached with torque-controlled wrenches that record every single fastener tightening. Everything is documented, every step photographed, every decision logged permanently. The first full assembly of a Mars rover takes months, and when it is done, the real work begins. The rover must be tested as a complete system, not just individual parts. It is driven across a simulated Mars terrain called the Mars Yard, an outdoor test facility at JPL filled with rocks, sand, and inclines designed to replicate Martian geography. Engineers watch every wheel turn, every sensor reading, every motor response, and they take notes on everything. Inside the thermal vacuum chamber, one of the largest in the world, The assembled rover is subjected to complete environmental extremes of space and Mars. The chamber drops to near absolute zero. Then it bakes at temperatures that would melt plastic. It cycles through these extremes hundreds of times, while every system on the rover continues to operate. If anything fails in this chamber, engineers are grateful, because failing here means it will never fail on Mars. Now, let's talk about the brain. Every Mars robot is controlled by a radiation-hardened computer called the R8750 processor. It runs at just 200 megahertz, about 100 times slower than the processor in your laptop. But speed is not the priority. Reliability is. This processor was designed to operate without failure for years in the hostile radiation environment of deep space. It has flown on over 100 space missions. Its failure rate is effectively zero. The software running on a Mars rover is equally extraordinary. It must allow the robot to make real-time decisions completely on its own, because commands from Earth take between 3 and 22 minutes each way to reach Mars, depending on orbital positions. By the time a human engineer says stop, the rover has already driven another half mile, so the rover's AI must think for itself. It must detect obstacles, assess terrain risk, and choose its own path, independently. This autonomous navigation system is called AutoNav. It processes stereo camera images in real time, builds a 3D map of the surrounding terrain, identifies hazards, and plots a safe driving path, all within seconds. The software running AutoNav took teams of programmers over a decade to develop and refine. On Perseverance's very first autonomous drive on Mars, it traveled farther in a single session than any previous rover had ever done in a week. That is the power of autonomous intelligence. But Mars robots are more than just rovers. JPL also builds orbiters, landers, helicopters, and specialized scientific instruments. The Ingenuity helicopter, the first powered aircraft to fly on another planet, was built at JPL and flew alongside Perseverance. It weighed just 1.8 kilograms. Its rotors spin at 2,500 revolutions per minute, 5 times faster than a helicopter on Earth. Because the Martian atmosphere is just 1% as dense as Earth's, that engineering breakthrough rewrote the rules of aviation. Back on the manufacturing floor, a new generation of robots is already taking shape. Engineers here are not building the next Mars mission. They are building the one after that, and the one after that. JPL plans its mission pipeline a full decade in advance. Components being fabricated today may not launch until 2032. The factory floor is always building toward a future that most people have not even begun to imagine yet. This is not reactive engineering. This is visionary engineering. One of the most secretive sections of the JPL facility is the Sample Return Vault. This is where hardware is being developed for NASA's Mars Sample Return mission, arguably the most ambitious robotic operation in history. The plan is to launch a rocket from the surface of Mars, rendezvous with an orbiter in Martian orbit, and return rock samples to Earth. To launch a rocket from another planet. Think about that. No human has ever done that from Earth without years of infrastructure. NASA plans to do it robotically on Mars. The Mars Ascent Vehicle, the rocket that will launch on the Martian surface, must be small enough to fit inside a landing craft, yet powerful enough to achieve Martian orbit. It must ignite in Martian temperatures without a launch pad, without a crew, and without a second chance. Engineers are testing propellant systems, guidance algorithms, and ignition mechanisms right now. If this works, it will be the most extraordinary thing a robot has ever done, anywhere, in all of human history. Here is a number that will put everything in perspective. The total cost of developing, building, launching, and operating a single Mars mission typically ranges from $2 to $3 billion. The Perseverance rover program alone cost $2.7 billion. That is over $250 million per year of the rover's planned mission life. Every part you see being built in this factory represents not just engineering. It represents an enormous bet on the future of humanity, a bet that NASA keeps winning. Now let us go deeper into the AI systems that are quietly transforming how these robots are designed and built. At JPL, artificial intelligence is not just installed in the final product. It is used throughout the manufacturing process itself. Machine learning algorithms analyze sensor data from machining operations and predict tool wear before affects part quality. AI systems scan camera footage from assembly lines and flag anomalies that human inspectors might miss. The factory is becoming as intelligent as the machines it builds. Machine vision systems at JPL use high-resolution cameras and deep learning models to inspect components with accuracy beyond human perception. A camera system can scan the surface of a circuit board in milliseconds and detect a solder joint that is off by just a few microns. These systems have reduced inspection errors by over 60% compared to manual inspection alone. They do not replace human engineers. They give human engineers superhuman eyesight. In the data control room, banks of monitors display real-time telemetry from every test operation happening in the facility. Engineers monitor thermal data, vibration signatures, electrical current draws, and software diagnostics simultaneously. Each data stream is compared against a digital model called a digital twin, a virtual replica of the physical robot that runs simulations in parallel with real-world tests. If the physical robot deviates from its digital twin, alarms sound. Engineers investigate immediately. Nothing goes unexplained. Smart sensors embedded throughout the manufacturing floor track environmental conditions, temperature, humidity, particle count, air pressure, and automatically adjust cleanroom systems to maintain perfect conditions. These sensors communicate with a central building management AI that learns seasonal patterns and anticipates changes before they occur. The cleanroom today practically manages itself. Engineers focus on the work that requires human judgment. The building handles everything else. Predictive maintenance is another area where AI is transforming JPL operations. Every machine on the manufacturing floor, every CNC mill, robotic welder, thermal vacuum chamber pump, is fitted with vibration and temperature sensors that feed data to predictive AI models. These models can detect the early signatures of mechanical failure up to 3 weeks before the failure would actually occur. Machines are serviced precisely when needed. Not too early, not too late. Downtime has dropped by nearly 40%. The energy demands of the JPL facility are enormous. Thermal vacuum chambers alone consume power equivalent to several city blocks. JPL has invested heavily in solar generation and battery storage systems to offset its carbon footprint. But there's a deeper reason for the energy focus. NASA's next-generation Mars robots are being designed to generate and manage their own power on the Martian surface using nuclear radioisotope thermoelectric generators. Understanding energy systems here directly informs how robots will survive the Martian night. Speed and efficiency metrics at JPL would surprise most people. The average time from initial concept approval to completed rover hardware takes approximately 5 years. That sounds slow, until you consider that every single component must be individually verified, documented, tested in extreme environments, and approved by multiple review boards. A commercial car manufacturer builds a new model in about 18 months. But a commercial car does not need to operate flawlessly in a place where no mechanic has ever set foot. JPL has also pioneered a manufacturing philosophy called test as you fly. Every component is tested in the exact configuration and conditions it will experience during its actual mission. A wire harness destined for a Mars rover is not tested lying flat on a lab bench. It is tested while installed in the rover, in the exact position it will occupy, at the exact temperatures it will experience. This philosophy eliminates the surprises that destroyed earlier missions and has become the gold standard for all deep space hardware. The rover software development process at JPL is equally rigorous. Code is written, reviewed, and tested through a process called verification and validation. Every software function must be demonstrated to work correctly under a defined set of test conditions before it can be integrated into the rover's flight software. The total software package for a modern Mars rover contains over 10 million lines of code. Every single line is accountable to someone. Every function has a test case. There are no exceptions. Quality control at JPL reaches a level of intensity that borders on philosophical. Engineers here speak about their work in terms of legacy. They know that the rover they are building today may still be operating on Mars 30 years from now. They know that students not yet born may be studying data collected by machines they are wiring together right now. That awareness, That sense of historical responsibility is not a poster on a wall. It is the culture of this place. It lives in every decision made on this floor. Now, the question the whole world is asking: what does the rise of robotic exploration mean for human jobs? At JPL alone, the shift toward AI-assisted manufacturing has transformed roles dramatically. Manual inspection positions have largely been replaced by machine vision systems. But the number of software engineers, AI specialists, and data scientists has grown by over 30% in the past decade. The message from JPL is clear. Automation does not eliminate work. It elevates the kind of work humans do. The industrial ripple effect of NASA's robot factory is enormous. Technologies developed at JPL for Mars missions have already made their way into medical imaging systems, autonomous vehicle navigation, environmental monitoring, and advanced materials manufacturing. The engineers who design systems tough enough for Mars end up teaching industries around the world how to build better, smarter, more reliable machines. NASA's investment in Mars robots is not just about space. It is an investment in the entire future of American industry. The economic impact of JPL and the broader NASA ecosystem in the United States is staggering. Studies estimate that every dollar invested in NASA generates approximately $7 to $14 in economic returns through technology transfer, job creation, and industry stimulation. The Mars robot program has directly supported hundreds of American companies across 30 states. From aerospace suppliers in Texas to semiconductor manufacturers in Arizona. When you fund Mars robots, you're funding American innovation at every level. The military implications of Mars robotics technology are also significant, though rarely discussed publicly. Autonomous navigation systems developed for Mars rovers have informed drone navigation research. Radiation-hardened electronics have applications in military satellite systems. Lightweight structural materials pioneered for space use are finding their way into next-generation defense platforms. The line between space exploration technology and national security technology has always been blurry. At JPL, they are practically the same research program. Now for the question that keeps some of the sharpest minds at NASA awake at night. As Mars robots become more autonomous, more capable of independent decision-making, at what point do we need to ask about their ethical boundaries? If an autonomous Mars robot discovers signs of microbial life and must decide whether to collect a sample without human input, who made that decision? A machine? A programmer from years ago? These are not science fiction questions. These decisions are being written into software right now. The next generation of Mars robots will be more capable than anything currently in operation. Engineers at JPL are developing robots with enhanced AI reasoning, multi-robot coordination, and the ability to 3D print repair components on the Martian surface. Some prototypes can already build rudimentary structures from simulated Martian soil. By the time humans arrive on Mars, possibly in the 2040s, a robotic construction crew may have already built the first shelter waiting for them. The robots will get there first, and they will prepare the way. Think about the sheer audacity of what is happening inside this building. Human beings, born on a single blue planet, never having left the solar neighborhood until just decades ago, are now building machines capable of exploring, analyzing, and preparing another world for habitation. Every robotic arm assembled here, every line of autonomous code written here, every wheel tested in a simulated Martian yard here. All of it is a declaration that we are not a species content to stay where we began. The machines being built inside NASA's robot factory will outlast the engineers who built them. Some of these robots may still be transmitting data back to Earth long after their creators have retired, grown old, and passed on. They will carry with them the fingerprints, literally, of the technicians who assembled them in white gloves in a sealed clean room in California. And they will do it on another planet, silently, tirelessly, perfectly. That is perhaps the most human thing about them. Mars is waiting, and the machines being built right now are almost ready. The next great chapter of human history will not be written by diplomats or generals or market forces. It will be written in the dust of a red desert by robots forged in a quiet factory in California, running software written by people who believe the impossible was simply a problem not yet solved. The countdown has already begun. And when those wheels finally roll across Martian soil, the world will never look at this planet the same way again. You've just gone inside the most extraordinary factory on Earth. The place where humanity's future is being assembled one bolt at a time. If this story moved you, if it made you see the stars a little differently, drop a comment below. Tell us what amazed you most. Share this with someone who needs to know the future is already being built. And subscribe to World Robot Factory, because we are just getting started. The machines are ready. The mission is live. And the next world is closer than you think.